Welcome back. I hope you had a great Thanksgiving. Didn't eat too much. I think I gained 5 pounds. Yeah, I had a good week. Today I'm going to give just a short introduction to communication systems. This, like what we did last time, could be a whole class. Okay, operating systems, a whole class. This could be multiple. This could be a whole discipline. Okay. And so I just want to introduce some terms. I guess it's probably my agenda here for this lecture. And to entice you, if you want to know more, go take some classes. We saw last time that the operating system is basically a layered device. And that is a separation between tasks, which are user functions, and physical hardware. But this field of communication fits into this same paradigm. In other words, it will be layered in a sense that when the tasks communicate with each other, they communicate. And when the operating system talks with other operating systems, they send messages. And when it gets down to the physical layer, whether that's wireless or wired, we can talk about frames. This is a 3-level hierarchy. They can be 4, 5, 6, 7, 8, 9 layers. It can be layered. And you remember the reason why a layered protocol is the right way to design. It's more complicated. That's bad. What does it allow you to do? Layered solution.
You can switch out the layers.
You can switch out the layers. So the task could communicate with each other regardless of whether this is wired or wireless, whether this is Wi-Fi or Zigbee. So we could switch out the layers. And we could switch out the operating system. It allows you to change and abstract. So those are the two. This layers is an example of abstraction. We can think about, when we talk about communication, it's first important to start with what are we communicating, and that's information. There are some to believe that in 50 years, electrical engineering will have taken over the business of information, whether you're encoding it, storing it, transmitting it. And so the knowledge or the managing of information is one of the forefronts that many people think is a wonderful future for electrical engineering. Okay. And so when we think about information, we can think about data. If you want to know an outbreak of disease, all you have to do is ask Walmart. Walmart knows when there's an epidemic about to happen because people start buying over-the-counter medicines. If you want to know about when a government is ready to be overthrown, you can just monitor the social media. Okay, so there's a lot of power in the data. But we're going to talk about the transmission of that data in today's lecture. But remember that this whole field has a wonderful future. Okay. Here's some terms. The encoding, or the taking of information and defining it in one way, is called coding or line coding, where we specify bits of information as either light, electromagnetic waves, voltage, current, etc. The other term that often happens is because, especially in the Wi-Fi field, we can't communicate at, there's no electromagnetic fields in the kilohertz range, so what we do is we modulate it at whatever 3 point whatever gigahertz, megahertz, and then pass that data inside of those sinusoids. It's important to know whether it works or not, and so the whole error detection and correction. And as you might imagine, in order to go faster, what we're going to do is we're first going to compress the data, keep the important stuff, throw out the extra bits, and then send the data and then decompress it. So this is a way to improve performance by compressing. Okay. Information will change form as it's communicated. And so we will see the data. If you look at a communication system, it's not all the same. The bits are going to change, especially if you compress it, then it changes. You encode it, then it changes. You can make, once you've divided into a representation, then it will change. Okay. Here's some examples of the size of various things. An image might be, on the order of thousands of kilobits. A color image may be millions. And so what we want to do is compress it. And so the compression ratio allows you to save space and save time. Here's some examples of some rates. Okay, and so again, we'll see in a couple of slides, but this issue of how fast we go is very important. If you want to tell who's on the other side of the phone, we're talking about a sampling rate of about 4,000 hertz, which gives you about 64,000 bits per second, uncompressed. If we want to go faster, we can take that same voice and compress it and save and put twice as much on there. If we're willing to wait a long time, we can take high fidelity audio, compress it a lot, and then send it or store it. And this is basically how we deal with music, how we deal with videos, and how we deal with television. Compression is the key to surviving these high bandwidth channels. Okay, because we don't have enough space to send gigabits per second, so we're going to compress it before we send it. All right. Some more terminology. The transmitter is obviously the out, and the receiver is the in, and the medium is here in the middle. And in 319K, for instance, we saw, how many wires did we take to do 319K? Lab 9?
2.
Nope.
3.
Lab 9 took 3 wires. Why? There were 3 wires in 319K Lab 9 where we took one launch pad here, one launch pad there, and we had what was called full duplex. A UART went this way, a UART went that way, and what's the third wire? Ground. Okay, because it's encoded as a voltage. If we wanted to send it with 2 wires, we could use something like fiber optics. Well, fiber optic, cables. We can do a fiber optic cable would allow you to send full duplex with 2 wires. Now, that's called a guided medium because it's a wire. You send the power to you send the energy, by the way, remember that? That's the name of the question. Energy down that wire, and it goes in the proper direction. You send light down the fiber optic cable, it goes where you tell it to go. Whereas Wi-Fi was an example of an unguided media because you send it out and it goes in all directions. Okay. I alluded to full duplex, which is in both directions. And when we talk about full duplex, we usually mean data, right? This is data being transmitted in one direction, 2 directions, okay, or both directions at exactly the same time. Okay? How do people talk? A polite room that you with a number of people in it. Most people talk in half duplex, communicate in half duplex. Okay, but if you've ever been around a bunch of Italians, right, full duplex, yeah, everybody talking. I'm not sure there's any listening going on. Full professors, simplex, right? We sometimes only talk, we don't listen. Okay, but it's important for you to understand the communication. Now, the word analog means analogous. And as we saw this before, this is the same thing as our sampling. If we have a continuous signal, both in amplitude and in time, then it's an analog signal. But discrete is both discrete in amplitude and in time. So discrete is both discrete in time and amplitude. Periodic is what you might think, that the wave doesn't have to be sinusoidal, but it repeats, and aperiodic, it doesn't repeat. Okay. As I promised, if does anybody have I squared C in their project? Yeah, and I'm about ready to tell you why it doesn't work. Okay. Because when I squared C is transmitting information down the wire, it never sends energy. And it turns out in order for, at least in lab 9 in 319K, at least half of your bits had energy in it. Okay, voltage and current, right? So energy, right? What's the definition of energy? You know, from joules, right? Energy is equal to what electrical properties? What times what? Let me start you out. If I added power here, what next parameter? How do I finish the equation? Power times time. Okay. If I used voltage, right, I'd have the voltage times current times time, and so the act of communication embodies this principle that you're going to take that data, create an energy packet, transmit that energy down the media, right, either guided or unguided, and that energy packet is going to attenuate, distort, and have added noise, and then hopefully your decoder will receive that energy packet and determine whether or not that bit was a high or low. So if you look at the serial port TX connected to an RX and the grounds are connected, okay? If you looked at a serial port communication, right? And there's the start bit, and there's the stop bit, and here's the data. How much energy got transmitted? Okay, how much energy is encoded in the bit? I gotta ask. You gotta tell you whether the bit's high or low. So if the bit were a 1, how much energy do you have? Oh, the voltage is easy, right? What voltage do you have? 3.3 volts, right? The time is easy, right? How much time do you have? Right, 1 over the baud rate. How much current do you have? Is there any current? It better be, right? Because if there were no current, no information would transfer. Okay? But you can think about it, and that is, there's a term you already know, right? So if I take an output if I take the output and this is sending a high, this guy is on, there's my wire, and where does it go? Where does this wire connect to on the other microcontroller? What physical device is inside the receiver in lab 9 of 319K, this UART? I'm connecting a UART to a UART here. Goes where? Goes into, right, the gate of a transistor. And now you can tell me how much current's going to flow. There's a term, right? We went over that. Is it a trick question? Is it IOH or is it IIH? How much current actually flows? What's the definition of IOH, by the way? It's the maximum available current that it can source. And what's the definition of IIH? The current it needs to be high. Okay? So IIH is the current that needs to drive this transistor here, In order, the gate current, it needs to drive it, whatever it is, that 2 microamps, whatever, it's in microamps. So you're going to have microamps of current. But you do have energy, by the way. Which means if you want to go faster, what are you going to have to do, by the way? Because if you go faster, what happens to the delta T? It goes smaller. If I want to go 10 times faster, okay, and I want to encode the bits as, okay, and the sad part is what happens when the bit is a 0? How much energy do I have? I'm going to have current flow, by the way. I'm going to have current flow. When the input is low, current will flow. Right? It's a comparison between the IOL and the IL. Current will flow. Microamps of current will flow. But how much energy do I have? None, because there's no voltage. Okay? No voltage. So if I want to go faster, what do I got to do? If I decrease the energy by a factor of 10, by decreasing the time, what do I have to do to make up for that loss? Increase the current, okay? Or the voltage, but the current's the easier one. Okay? And so there is a protocol which allows you to put a driver here and a decoder there, which will convert 3.3 into minus 6 volts and convert 0 into plus 6 volts. And it's wonderful. This is the RS-232 protocol. It's wonderful for the following 2 reasons. Okay? Why is plus or minus 6 better than 0 and 3? I'm driving twice as much current. I'm driving twice as much current because I'm always driving energy, right? Minus 6 drives, plus 6 drives. Okay? So you always want to look for the energy in the packet. The other reason it's better is because it will drive more current. Okay? And therefore, I will be able to send it down a long wire very fast. And so if you want to go even faster, right, I'm going to need even more current. So remember that the ability to communicate is about energy. Let me teach you one more important factor. Okay, bandwidth is suffice it to say, I will not ask you what the bandwidth of a communication system is, because there are 1, 2, 3, 4, 5, 6 definitions of bandwidth. Put that as a star in your to-do list. That bandwidth is one of those things that's got 6, 10 definitions. So be very, very careful. It's one of those things that goes in your requirements document. When I say bandwidth, I mean this. Okay. Now, if I do ask you on the final, what I mean is number of data bits transmitted per second. That's what Valvano means. But in terms of the communication field, there's a lot of definitions for bandwidth. Yes, there's a lot of definitions, and okay. So what I'd like to do for you is to prove a wonderful. I'm going to prove to you a wonderful theorem associated with with communication. Okay, so I'm going to make a following sort of approximation. Okay. When I communicate, okay, there is going to be, it's called a bandwidth, okay, but what I'm going to tell you is there will be a certain epoch in time that I can send data. All right, so now, if this time is delta t, how many bits per second am I transmitting? Do you know yet? What do I got to tell you to get the number of bits per second being transmitted? I told you the delta t, right? Millisecond, microsecond, something. What do you need to know to get bits per second? How fast does this thing run? What do I got to tell you? How many bits in the data? Okay. If I tell you it's 4 bits, now you know exactly, right? So if I tell you this is 1 millisecond and this is 4 bits, you know exactly that you're sending 4,000 bits per second, right? Now the question now comes is if I have a wire, and it doesn't matter whether it's guided or unguided, okay? And I'm going to send these data on this wire, on this media. I'm going to send it from the transmitter to the receiver. How many bits can I encode in that wire? So for instance, let's just do a simple thing that you understand. What if this were a voltage between 0 and 3 volts? It's a voltage, and I'm going to send that voltage. Okay. Now it might be on top of a carrier, right? So so there's my voltage, and the amplitude of that voltage is encoded. I'm going to encode the data bits, those 4 bits of data, onto that amplitude. Okay? And I'm going to transmit it down. So how many bits can I stick in there? Thousands, millions, billions. No, what happens?
They get too close to each other.
They get too close to each other. Okay, so now what I want to do is draw this. Let's just draw. We'll see. Okay. Oops, I don't want magenta. And I said 4 bits, so I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so now there are 16 different levels that I could select from to get me my 4 bits. Okay? But what happens if I have this much noise? What happens? Well, if that's what my signal is, which one is it? Right? Is it this one, or is it that one? Or is it this one? I can't tell, right? The noise, so there's a magic word that tells you how many levels of resolution that I can get out of this encoding. Right? Would you love to have it look like this, right? Right? So you say, now that's going to work, right? Because the noise is less than my bin size. And so the key parameter to distinguish how many bins do I have would be what formula? The number of bits in the data is approximately analogous to what parameter? Okay, well, that is the precision. The precision, okay, this is that's the definition of precision. But in this particular thing where I've told you what the noise is, what other parameter do you need to know in order, because if I just tell you it's 50 millivolts, that's not the right answer. Not enough. What do you need to know? If I said 50 millivolts, could you answer how many bits it is? Sure. If the noise is 50 millivolts, how many bins do I have? Do you see the other volt? You see the other parameter in my equation? See it? The 3, yeah, the range. Okay? And so what I need to tell you is the number of bits is going to be log base 2 of the signal to noise ratio. Okay? So in essence, in the essence of encoding this data is, can I distinguish it on the way out? Okay. So in order for me to determine what the best case scenario for communication is, I need to know two pieces of information. Well, two pieces of information. I need to know how often is the data transmitted, and I need to know the signal-to-noise ratio. And somebody famous came up with a theorem. And there's the picture I just drew. And that's called the Shannon Channel Capacity. Okay? And this term W here, okay, is the number of packets per time that I'm sending. Okay? So if I'm sending 3,400 packets per second, and the signal-to-noise ratio is 6,000, okay, which tells me I'm going to send about how many bits per packet is that? By the way, if this is precision and alternatives, how many bits in a packet? See that? What's the significance of 4,096? That's 2 to the 12th, right? What's the significance of 8,192? Right, it's 2 to the 13th. So what is 6,010? Somewhere between 12 and 13 bits. Okay, more precisely 12.62 bits. You know, hey, how can you send a half a bit? Well, I got power, so I can send a half a bit. Right? This is a theorem, right? So we can send half a bits in a theorem. And so what we're going to do is we're going to take the signal-to-noise ratio here and convert it to from decibels into precision in alternatives, and that, well, this is already in this one here is in alternatives, and this is going to tell me the number of bits, and that's going to tell me the number of, and so the question about whether you remember the rule about using 10 or 20? Right? If the encoding is power or energy, whatever, in this case power, we're going to use 10. If it's voltage, we're going to use 20. All right. So I've told you two things that I think you ought to remember. Okay? Let me summarize. The first is when we transmit, we're going to encode the information in energy, transmit it across space, and decode it. Okay? And the second is what matters are how many packets per time can I send? What's the encoding packet time? And how many bits can I put in each of those packets? And that's called the Shannon Channel Capacity. And both of those, or one of those, will be on the exam. Okay? Questions on communication?